In the deep sky, far from the grand spirals and giant ellipticals, there is a small and quiet system that should have gone unnoticed. At its centre, however, NGC 4395 hides an oversized secret, a supermassive black hole buried inside one of the tiniest known galaxies of its kind. Tonight we explore how such a modest galaxy came to host such an enormous heart, and what this mismatch reveals about how black holes and galaxies grow together. If you enjoy calm journeys to strange corners of the cosmos, please subscribe and share, and tell us in the comments what surprises you most about a supermassive black hole living in such a tiny galaxy. Thank you for watching. Now, let's begin. In the nearby universe around the Milky Way, galaxies assemble into small groups and loose clouds, rather than forming a smooth uniform distribution, and NGC 4395 is one member of this structured region. Astronomers often refer to the space within a few tens of millions of light-years of the Milky Way as the local volume, a domain where the overall expansion of the universe is already evident, but where the pull of gravity from nearby matter still organizes galaxies into recognizable systems. Within this volume lie the local group which contains the Milky Way and the Andromeda Galaxy, as well as several other associations such as the Canes-Venatici clouds and the group centered on the galaxy NGC 4631. NGC 4395 resides in the direction of the constellation Canes-Venatici, at a distance of roughly 10 to 15 million light-years from Earth, placing it outside the local group but still firmly inside the nearby universe that can be studied in great detail with modern telescopes. At these distances, light from a galaxy takes on the order of 10 million years to arrive at Earth, so observations capture these systems as they were in the relatively recent cosmic past, long after the main era of galaxy formation, but still within the ongoing evolution of groups and clouds. In this scale range, the large-scale structure of the universe can be described as a cosmic web, in which galaxies and their dark matter halos trace out filaments, sheets and nodes, leaving wide, comparatively empty regions between them. The Canes-Venatici structures form part of this web as a low-density concentration of galaxies, with a total luminosity lower than that of more prominent nearby groups, but still bound together by a shared dark matter halo. Studies of this region using distance indicators applied to individual stars resolved in several member galaxies have mapped out the three-dimensional distribution of systems and have shown that NGC 4395 lies toward the outskirts of a cloud rather than at the center of a rich cluster. In contrast to massive clusters such as Virgo, where hundreds or thousands of galaxies occupy a relatively compact region of space, the Canes-Venatici clouds contain fewer galaxies and show larger separations between individual systems, yet still display a coherent pattern of motions that marks them as a gravitationally bound configuration. In this environment, some galaxies are moderately bright spirals and irregulars, while others are faint dwarfs with low surface brightness, and together they provide a sample for examining how galaxy properties depend on both mass and surroundings. NGC 4395 is one of the fainter spiral systems in this setting, contributing only a small fraction of the total starlight in the cloud, but its proximity makes it an important target for detailed observation. The broader environment around NGC 4395 has been reconstructed by combining radial velocity measurements with accurate distance estimates. Radial velocities derived from the shift of spectral lines show how galaxies move along the line of sight, while distance indicators based on resolved stellar populations give their actual positions in space. For several galaxies in the Canes-Venatici region, astronomers have used methods such as the tip of the red giant branch technique, in which the brightness of the brightest evolved red stars provides a standard candle once the population is well measured. By comparing these distances with radial velocities, researchers can separate the smooth expansion of the universe from additional motions produced by the gravity of groups and clouds. In this framework, NGC 4395 and its neighbours help define the mass and dynamical state of the Canes-Venatici structures. Analyses of these data suggest that the total mass of the cloud, including dark matter, is significantly greater than would be inferred from the starlight alone, leading to relatively high mass-to-light ratios compared with some other nearby groups. This indicates that a large fraction of the matter in the region is not in the form of luminous stars or gas, which is consistent with the general picture that dark matter dominates the mass budget of galaxy systems on these scales. The local volume around NGC 4395 has also been used to refine the calibration of the cosmic distance scale, because many galaxies in this radius can be observed with both ground-based observatories and space telescopes such as the Hubble Space Telescope. Multiple distance methods can be applied and compared, reducing systematic uncertainties. Cepheid variable stars' surface brightness, fluctuation measurements, and the tip of the red giant branch all contribute to a network of cross-checked distances. NGC 4395 itself, while of relatively low surface brightness, is close enough that its stellar content and star-forming regions can be resolved and used as part of this calibration work, anchoring its position within the local volume with reasonable precision. On the sky, NGC 4395 appears in a region that is not dominated by a single overwhelmingly bright central galaxy. Instead, the Canes-Venatici associations show a more modest hierarchy in which several galaxies of intermediate luminosity share the role of principal members. This contrasts with groups like the Local Group, where the Milky Way and Andromeda clearly dominate, or with rich clusters, where a handful of giant ellipticals contain a large fraction of the stellar mass. In the Canes-Venatici region, the distribution of galaxy masses and types is more even, and NGC 4395 fits into this pattern as a dwarf spiral whose overall mass and luminosity are well below those of the largest members, but still high enough to be studied in depth. The local cosmic context of NGC 4395 thus combines three key aspects. First, it is part of the nearby universe, where individual stars and detailed structures can be resolved, allowing direct tests of distance indicators and stellar population models. Second, it inhabits a low to moderate density galaxy cloud, rather than a rich cluster or complete isolation, providing an example of how galaxies evolve in a relatively gentle environment, where strong tidal interactions are less frequent but still possible. Third, it contributes to the mapping of the cosmic web on small scales, helping define the boundaries, mass and kinematics of the Canes-Venatici structures through its position and motion. From this perspective, NGC 4395 is not just an isolated faint patch of light in the sky, but one node in a carefully charted network of nearby galaxies whose properties and mutual relations inform models of structure formation and galaxy evolution. NGC 4395 belongs to a modest galaxy concentration in the direction of the constellation Canes-Venatici, where several small groups and clouds of galaxies trace a fragment of the nearby cosmic web. On these scales, galaxies are rarely completely isolated. Instead, they sit in shared dark matter halos whose gravity organizes them into bound associations with characteristic sizes of a few million light-years and internal motions of a few tens to a few hundreds of kilometers per second. The surroundings of NGC 4395 illustrate this pattern in a low-density environment. Distance measurements place NGC 4395 at roughly 10 to 15 million light-years from Earth, and similar techniques applied to neighbouring galaxies in the same part of the sky reveal a loose aggregation with comparable distances and related radial velocities. This set of galaxies is sometimes described as part of the Canes-Venatici cloud itself, one segment of the local network of groups that includes the Local Group and other nearby associations. In contrast with rich clusters where hundreds of galaxies fill a region only a few megaparsecs across, and the intra-cluster medium is a hot, dense plasma, the environment of NGC 4395 contains fewer members and a more tenuous intergalactic medium. X-ray observations of this region do not show a bright extended halo of hot gas comparable to that in massive clusters, which is consistent with expectations for a system of relatively low total mass. Instead, the space between galaxies is thought to be filled primarily with diffuse, warm-to-hot gas and dark matter, whose presence is inferred indirectly from the motions of the galaxies. Within this context, NGC 4395 is one of several late-type systems with significant gas content and ongoing star formation. Its neighbours include other small spirals and irregulars whose morphologies and star-forming properties suggest a relatively gentle, evolutionary pathway compared with galaxies that have experienced strong interactions in dense clusters. The distribution of morphological types in this region is skewed toward gas-rich star-forming galaxies rather than gas-poor ellipticals and lenticulars, which is a common feature of low-density environments, where processes such as ram pressure stripping by a dense intracluster medium are weak or absent. The velocities of galaxies around NGC 4395, measured from the Doppler shift of their spectral lines, provide information about the gravitational potential of the group. When these velocities are combined with distance estimates, astronomers can determine whether the system is gravitationally bound and estimate its total mass including dark matter. For the Keynes-Venatity cloud and related structures, such analyses yield mass-to-light ratios that indicate a substantial dark matter component, but not at the extreme level observed in some very faint groups. The galaxies move with modest peculiar velocities relative to the smooth expansion of the universe, consistent with a system that has not yet fully relaxed into a compact configuration. This is reflected in the relatively large separations between individual members. NGC 4395 does not sit at the dynamical centre of a dense core, but rather occupies a position that can be described as peripheral within the broader cloud. The tidal field produced by the group is therefore weaker than in the cores of rich clusters, and major tidal interactions or mergers are expected to be less frequent. Nevertheless, even in such low-density settings, minor interactions and the cumulative effect of the group potential can influence gas accretion and star formation over long timescales. Observations of neutral hydrogen in and around galaxies in this region show extended gas envelopes and in some cases filamentary structures that may represent gas flows within the group environment. For NGC 4395, mapping of neutral hydrogen reveals that its gas disk extends beyond the optical disk defined by starlight, a feature shared with many late-type galaxies. The interaction between this extended gas and the group environment can affect the rate at which gas settles into the inner disk and becomes available for star formation. On larger scales, the position of the Keynes-Venatity structures within the local supercluster environment ties NGC 4395 indirectly to more massive assemblies. The local supercluster dominated by the Virgo cluster and its surroundings contains many filaments and clouds of galaxies that channel material into the central mass concentrations. The Keynes-Venatity cloud is one of these features, and its galaxies, including NGC 4395, participate in the overall flow of matter toward the supercluster center. This motion manifests as deviations from the pure Hubble expansion when radial velocities are compared with distances. Such flows are modest in amplitude at the distance of NGC 4395, but they are important for constraining models of the distribution of dark matter on scales of tens of millions of light-years. From a multi-wavelength perspective, the environment of NGC 4395 has been explored in optical, radio and infrared surveys. Optical imaging catalogues the morphologies and luminosities of group members, showing that NGC 4395 is among the less luminous spirals but still brighter than many dwarf irregular companions. radio observations trace the neutral hydrogen content of the group and identify galaxies with extended gas reservoirs or signs of disturbance in their velocity fields. Infrared data from space-based observatories probe the dust content and low-level star formation in both NGC 4395 and its neighbours. Together, these datasets support the view that this is a low to moderate density environment where gradual processes dominate over rapid, violent transformations. In such surroundings, galaxies like NGC 4395 can retain their gas over long intervals, allowing prolonged low-intensity star formation and the maintenance of a late-type morphology. The group environment also provides a potential supply of intergalactic gas that can be accreted onto galaxy disks, and in some cases directed toward their central regions. For NGC 4395, this broader context is relevant because its active nucleus and central black hole require a continuing, though modest, inflow of gas to sustain their emission. While the details of that inflow are set by processes within the galaxy itself, the availability of gas and the absence of disruptive cluster-scale mechanisms are shaped by the galaxy's membership in this loose cloud. The cosmic environment of NGC 4395 is therefore characterized by a relatively small number of companion galaxies, a dark matter halo of moderate mass, a weak but non-negligible tidal field, and a supply of gas that is sufficient to maintain star formation and nuclear activity at low levels over extended periods. NGC 4395 is classified as a late-type dwarf spiral galaxy, and its basic global properties can be understood most clearly when it is set beside more massive spirals such as the Milky Way or typical bright members of nearby groups. A spiral galaxy is usually described in terms of its stellar disk, its gas content, and often a central bulge which together determine its overall luminosity scale and appearance on the sky. In large systems, the stellar disk extends for many tens of thousands of light-years and contains a high surface density of stars so that even relatively short astronomical exposures reveal a bright, well-defined structure. By contrast, NGC 4395 has a much smaller stellar mass and a more compact disk. Its starlight is distributed over an area that is modest in physical size compared with a giant spiral, and the mean surface brightness of that disk is significantly lower. As a result, when observed in visible light, the galaxy appears faint and patchy, with its structure becoming clear only in deeper images that integrate light over long times. This combination of low total luminosity and low surface brightness places NGC 4395 in a regime that is intermediate between the bright spirals that dominate rich groups and the extremely diffuse low surface brightness galaxies that are barely detectable in wide-field surveys. The difference in stellar mass between NGC 4395 and a large spiral like the Milky Way affects many aspects of their observable properties. In a massive spiral, the gravitational potential produced by stars' gas and dark matter supports a disk that rotates rapidly with characteristic circular velocities of a few hundred kilometers per second. The high mass and rotation speeds correlate with high luminosity and with well-developed spiral arms that can be traced continuously around the disk. In NGC 4395, the lower mass leads to lower rotation speeds and a weaker overall gravitational field in the visible regions of the galaxy. Measurements of its rotation curve indicate that the circular velocities in the outer parts of the disk are significantly lower than in giant spirals. This is consistent with a galaxy occupying a smaller dark matter halo and containing fewer stars. The spiral structure of NGC 4395 is also less regular than in grand design spirals. Instead of 2 or 3 long continuous arms, the disk shows multiple short segments and irregular features with star-forming regions and clusters arranged in a more scattered pattern. This is typical of low-mass, late-type spirals, and reflects differences in how spiral density waves and local gravitational instabilities operate in such systems. Surface brightness, which describes the amount of light emitted per unit area on the sky, is another key parameter in comparing NGC 4395 with larger spirals. Bright spirals usually have central regions and inner disks with high surface brightness, meaning that their starlight stands out clearly against the background sky, even at moderate telescope apertures. In NGC 4395, the disk surface brightness is low across a wide range of radii. This implies that the surface density of stars is low, and that much of the disk is dominated by relatively faint stellar populations. From a practical observational standpoint, this means that NGC 4395 is more challenging to study in detail because resolving its structure requires long exposure times and careful subtraction of the sky background. However, its proximity partially compensates for this, allowing instruments, such as the Hubble Space Telescope and large ground-based observatories, to resolve individual stars in its disk and to map its star-forming regions despite the low surface brightness. The presence or absence of a central bulge represents another fundamental difference between NGC 4395 and many larger spirals. In galaxies like the Milky Way, a central bulge of old stars contributes a substantial fraction of the total stellar mass and creates a bright, roughly spheroidal component at the center of the disk. This bulge is associated with a high central stellar density and often with a distinct kinematic structure. Observations of NGC 4395 in contrast show no evidence for a classical bulge. The central light profile can be explained with a continuation of the disk, plus a compact nuclear component associated with its active core, but there is no massive spheroidal stellar component with the properties of a traditional bulge. This places NGC 4395 among the class of bulgeless or nearly bulgeless spiral galaxies. Such systems are of particular interest because many empirical correlations between central black hole mass and galaxy properties, such as the relation between black hole mass and bulge, stellar velocity dispersion, have been derived for galaxies with well-developed bulges. NGC 4395 provides a contrasting case where an actively accreting central black hole resides in a galaxy that lacks a prominent bulge. When compared with other dwarfs, NGC 4395 is unusual because of its combination of low mass and nuclear activity. Many dwarf spirals and irregular galaxies in the local universe do not show clear signs of an active galactic nucleus, and their central regions are dominated by star formation or by relatively quiescent stellar populations. In NGC 4395, spectroscopic observations reveal broad and narrow emission lines and variable continuum emission from the nucleus, indicating the presence of an accreting central black hole. The overall luminosity of this nucleus is low compared with the active cores of luminous Seyfert galaxies and quasars, but it is significant relative to the modest stellar output of the host. This means that in some wavelength ranges, the active nucleus contributes a non-negligible fraction of the total light from the central regions. The host galaxy therefore provides an example of a low-mass, low-surface brightness spiral, where the central engine is detectable and can be studied in the context of a relatively simple stellar structure. The environment within the galaxy further distinguishes NGC 4395 from larger spirals. In massive systems, the central bulge and dense inner disk can regulate gas inflow toward the nucleus through bar-driven torques or other dynamical features. In NGC 4395, the absence of a strong bulge and the presence of a more irregular spiral pattern imply that the mechanisms bringing gas into the inner few hundred parsecs may differ in detail. Gas flows may be governed more by local instabilities, stochastic processes, or the cumulative effect of small-scale asymmetries in the disk, rather than by a single strong bar or global wave. Observationally, the star formation rate in NGC 4395 appears modest, and the distribution of star-forming regions is patchy, rather than concentrated in a well-defined ring or bar-driven inflow pattern. This supports the view that its evolution is dominated by low-level extended processes rather than by the dramatic central starbursts sometimes seen in more massive galaxies undergoing strong interactions. The overall shape of NGC 4395 is that of a faint irregular spiral system, whose main stellar component occupies a relatively thin disk with loosely wound arms and a patchy distribution of light. Deep optical images show a central region from which several fragmented arm segments extend, rather than a pair of long continuous arms that wrap smoothly around the galaxy. These segments contain knots of enhanced brightness, associated with groups of young stars and ionized gas, while the underlying disk light remains diffuse and of low surface brightness. The spiral pattern is classified as late type, with features that resemble those of Magellanic spirals, in which the arm structure is less regular and less symmetric than in grand design spirals. The stellar disk of NGC 4395 extends over a modest physical size compared with bright spirals, but within that area the distribution of luminosity is far from uniform. Regions with noticeable star formation contrast with large, more quiescent patches where the starlight is smoother and dominated by older populations. The galaxy is viewed at a moderate inclination, not exactly face-on and not edge-on, so the disk appears as an oval rather than a perfect circle. This orientation allows the spiral pattern and arm fragments to be traced without severe line-of-sight confusion from overlapping structures. The thickness of the disk inferred from the vertical distribution of light and from the kinematics of gas and stars is relatively small compared with its radial extent, consistent with a late-type spiral where the vertical gravitational field is dominated by a combination of the stellar disk and the surrounding dark matter halo. Isophotes, which are contours of equal surface brightness, provide a quantitative description of the light distribution. In NGC 4395, these isophotes are not perfectly elliptical. Deviations from simple elliptical shapes reflect the clumpy arms and star-forming regions that perturb the light profile. At low surface brightness levels, the outer isophotes appear more regular and roughly elliptical, tracing the envelope of the stellar disk. Closer to the center, the isophotes become more irregular due to the influence of bright star-forming complexes and the compact nuclear source. The radial surface brightness profile of the disk can be approximated by an exponential decline, a common feature among spiral and dwarf disk galaxies, but with parameters that place NGC 4395 on the low surface brightness end of the distribution. The scale length which characterizes how rapidly the brightness falls with radius is such that the disk fades gradually over several scale lengths before blending into the background sky. This gentle decline means that the galaxy has an extended faint component that can be detected only with sufficient depth in imaging. The outer parts of the disk are dominated by this low-level light, with only occasional small associations of young stars marking local enhancements. As a result, the contrast between arm segments and interarm regions is moderate rather than extreme. The spiral pattern itself is not symmetric about the center. One side of the galaxy shows more prominent arm fragments and brighter associations of young stars, while the opposite side is less strongly marked. This asymmetry may be related to small-scale perturbations in the disk, minor past interactions or internal processes that redistribute gas and stars in a non-uniform way. In dwarf spirals such as NGC 4395, the shallower gravitational potential and lower rotational shear can make the disk more susceptible to local disturbances that break strict symmetry. The irregularity of the spiral structure is evident in both the distribution of H-alpha emission, which traces ionized gas around young massive stars, and in broadband images that show the combined light of stars of various ages. Despite these irregularities, the global classification as a spiral is secure because the disk component and the overall sense of ordered rotation are clear in kinematic data. The central region of NGC 4395, as seen in broadband images, consists of a compact light concentration embedded in the inner disk, but the transition from the outer disk to this central area is gradual in terms of surface brightness. There is no sharp boundary between a bright spheroidal bulge and a fainter disk. Instead, the disk continues inward with increasing prominence of small-scale structures and the nuclear source as one approaches the center. The nuclear region contributes a point-like component in high-resolution images associated with the active galactic nucleus, but in terms of the global morphology, the galaxy retains a disk-dominated structure. Bars, which are elongated stellar features that can redistribute angular momentum and drive gas inflows in many spirals, are not prominent in NGC 4395. Some studies have searched for weak bar-like distortions in the inner isophotes, but any such features are subtle compared with the clear, strong bars observed in many larger spirals. The absence of a strong bar is consistent with the relatively simple dynamical structure inferred from the rotation curve and with the low overall mass of the galaxy. In the absence of a strong bar, the spiral arm fragments and local asymmetries become the main non-axis symmetric features in the disk. On the sky, NGC 4395 occupies a small angular size reflecting its modest physical dimensions and its distance of roughly 10 to 15 million light-years. Within this small area, however, the combination of low surface brightness and structural complexity means that different observational setups emphasize different aspects of the galaxy. Short exposures with moderate telescopes may reveal only the brighter inner regions and the most obvious arm segments, giving the impression of a compact irregular system. Deep exposures and large aperture instruments uncover the extended faint disk and the full extent of the spiral pattern, confirming that the galaxy is a disk system with loosely organized arms rather than a purely irregular object. The overall morphology in multiple bands confirms that NGC 4395 is a late-type spiral with an extended faint disk, fragmented spiral arms, and a compact nucleus embedded in a low-density environment where external perturbations are present but not dominant. In NGC 4395, the defining global photometric property is the low surface brightness of its stellar disk, which influences how the galaxy is detected, measured and interpreted in nearly every observing band. Surface brightness describes the amount of light received per unit area on the sky, and for this galaxy the values in the disk are significantly lower than in typical bright spirals of similar apparent size. In practice, this means that when NGC 4395 is observed with short exposures or modest instruments, only the highest contrast structures stand out clearly. The bright knots of star formation and the central light concentration are visible, while the extended disk that connects them remains near the limit of detectability. Deeper exposures with long integration times and careful control of background subtraction reveal that these isolated patches are embedded in a continuous but faint stellar component. The disk light declines gradually with radius approximately following an exponential profile, but with central and characteristic surface brightness values that place NGC 4395 at the faint end of the spiral galaxy population. This low surface brightness affects not only visual impressions, but also quantitative measurements of global properties such as total luminosity and stellar mass, because a significant fraction of the galaxy's light resides in low-level outskirts that can be missed if observations do not reach sufficiently faint limits. Multiband imaging shows that the low surface brightness disk is not uniform in color. Inner regions of the disk tend to appear somewhat bluer, reflecting a higher proportion of relatively young stars and ongoing star formation, while the outer disk is redder and dominated by older stellar populations with lower specific star formation rates. Even so, the overall colours of NGC 4395 indicate that it is still a star-forming system, not a quenched galaxy. The combination of low surface brightness and ongoing star formation places it among late-type dwarfs that evolve slowly, with a steady but modest conversion of gas into stars over long timescales. Photometric studies that decompose the light into radial bins find that the surface brightness changes gently with radius without sharp breaks that would indicate a strong truncation or a distinct outer component. Instead, the stellar disk fades in a continuous way until it merges with the sky background. This behavior suggests that whatever processes have built the disk, whether through gradual gas accretion or internal redistribution of angular momentum, they have operated in a relatively smooth fashion rather than through highly disruptive events that would leave strong features in the light profile. From a dynamical perspective, the low surface brightness implies that the gravitational potential in the visible disk is dominated more by dark matter and gas than by stars. In high surface brightness spirals, the inner rotation curve can often be explained largely by the contribution of the stellar disk, while in galaxies like NGC 4395, the stellar mass density is too low to account for the observed rotation speeds on its own. This leads to the conclusion that dark matter provides a large fraction of the gravitational support, even in regions where the stars are most prominent in the light distribution. Such systems are important for testing models of dark matter, halos, and disk stability, because the balance between dark matter gas and stars differs from that in more luminous spirals. The faintness of the disk also introduces selection effects in surveys. Traditional galaxy catalogues, especially those based on photographic plates or shallow digital imaging, are biased towards systems with higher surface brightness, which are easier to detect above the sky. NGC 4395 is bright enough in total light and close enough in distance to be well represented in local samples, but its extended outer disk would be less prominent in more distant analogues. Understanding galaxies like NGC 4395 therefore informs estimates of how many low surface brightness systems might be missing from more distant surveys, and how this hidden population contributes to the overall baryonic and dark matter content of the universe. In the context of the galaxy's own structure, the low surface brightness disk contains both diffuse older stars and localized enhancements, where young stellar associations reside. High-resolution imaging reveals that in many parts of the disk individual stars can be resolved, allowing color magnitude diagrams to be constructed and star formation histories to be inferred. These diagrams show sequences corresponding to red giant branch stars, main sequence stars, and in some locations blue helium burning stars, providing evidence for continuous star formation across a wide range of ages. The presence of older red giant stars at large radii indicates that the low surface brightness outskirts are not recent additions, but have been in place for a long time, built up through extended star formation and redistribution of stars rather than through a single recent accretion event. The gas associated with the disk, traced by neutral hydrogen observations, extends even beyond the faint stellar component, reinforcing the view that NGC 4395 has a substantial reservoir of material available for future star formation. Within the optical disk, the correlation between gas column density and surface brightness is not one-to-one, but regions with higher surface brightness often coincide with higher gas densities and stronger current star formation. The low overall gas surface density in many parts of the disk likely contributes to the low surface brightness, because the star formation rate per unit area depends on gas density through empirical relations. In NGC 4395, the gas densities are high enough to sustain star formation, but not so high as to drive intense starbursts that would raise the surface brightness of the disk dramatically. Instead, the system maintains a diffuse appearance with modest star-forming regions superposed on a faint background of older stars. Observationally characterizing the low surface brightness disk of NGC 4395 requires careful techniques to remove foreground stars from the Milky Way and background galaxies that project along the line of sight. Because the intrinsic brightness per unit area is low, contamination by unrelated sources can distort measurements of the galaxy's true light distribution if not properly accounted for. Modern studies use a combination of wide-field imaging to capture the full radial extent of the disk and high-resolution imaging to classify and subtract foreground and background sources. Once this is done, the underlying light profile of NGC 4395 can be mapped to very faint levels, revealing the full extent of the disk and confirming its classification as a low surface brightness spiral. The result is a picture in which the galaxy's main stellar component is extended diffuse and dominated by low-intensity emission, contrasted with a small number of brighter regions where recent star formation adds local enhancements to an otherwise faint disk. Star-forming regions in NGC 4395 appear as a scattered network of compact and diffuse emission zones distributed across the low surface brightness disk, rather than as a single dominant complex or a sharply defined ring. In optical images taken through filters that isolate hydrogen recombination lines, these regions emerge as discrete patches where ionized gas surrounds recently formed massive stars. Ultraviolet observations reinforce this picture by highlighting concentrations of young hot stars that have ages of only a few tens of millions of years. When combined, these traces show that star formation in NGC 4395 proceeds in many small sites spread over the disk, with no single location accounting for a large fraction of the total newly formed stellar mass. The typical sizes of individual ionized regions in NGC 4395 are on the order of a few tens to a few hundreds of light-years, comparable to or somewhat smaller than classical H2 regions in more massive spirals. Spectroscopy indicates that these regions are photoionized by short-lived massive stars whose radiation maintains the gas at temperatures of several thousand to around 10,000 Kelvin. The emission line ratios and derived oxygen abundances place NGC 4395 among low-mass systems with relatively low metallicity, although not at the extremely metal-poor end of the dwarf galaxy population. This chemical state is consistent with a long history of modest star formation in a shallow potential well where metal-enriched gas can more easily escape into the circumgalactic environment. The star-forming regions are not distributed uniformly with radius. They are more frequent and more luminous in the inner and intermediate parts of the disk and become rarer and fainter at larger radii where the gas surface density declines and the stellar disk is dominated by older populations. This radial trend agrees with empirical relations between gas density and star formation rate surface density. In NGC 4395, the gas densities rarely reach the high values seen in starburst galaxies, so the local star formation rates remain modest, even in the more active zones. The absence of a sharply peaked central starburst and the lack of a strong bar mean that the inner few kiloparsecs do not show the intense centrally concentrated star formation found in some more massive spirals. Instead, enhanced activity occurs in fragmented arm segments and in small complexes that form where local instabilities compress the gas. From the point of view of integrated properties, the total star formation rate in NGC 4395 is low in absolute terms, but non-negligible when scaled by the galaxy's small stellar mass. Estimates based on hydrogen recombination lines, ultraviolet luminosity and infrared dust emission converge on values that correspond to the formation of only a small fraction of a solar mass of stars per year. The exact value depends on the assumed initial mass function and the treatment of dust attenuation, but in all cases the global rate is well below that of a typical giant spiral. When expressed relative to its stellar mass, however, NGC 4395 shows a specific star formation rate that is consistent with other late-type dwarf galaxies on the star-forming main sequence. It is neither a starburst system nor a quenched galaxy, but rather a representative example of slow, continuous growth. High-resolution imaging resolves many of the star-forming regions into compact clusters and loose associations. Color magnitude diagrams constructed from these stars show sequences corresponding to young main sequence stars and blue helium burning stars whose relative numbers constrain the ages of the stellar populations. In many cases, the data indicate ages of only a few million to a few tens of millions of years. The clusters are generally low to intermediate in mass, lacking the extremely massive young clusters that sometimes form in the dense environments of interacting galaxies. This difference reflects the lower gas surface densities and weaker global perturbations in NGC 4395, which favour the formation of smaller, more numerous clusters rather than a few very massive ones. This spatial correlation between star-forming regions and the distribution of atomic gas provides further insight into the regulation of star formation. Neutral hydrogen maps show that NGC 4395 possesses an extended gas disk with local enhancements where the column density rises above a threshold level. Star-forming regions tend to coincide with these higher density patches, although not every gas peak hosts strong current activity. This pattern is typical of galaxies where local conditions such as gas turbulence shear and magnetic fields modulate the global relation between gas density and star formation. In NGC 4395, the absence of strong spiral density waves means that star formation is less organized into continuous arms and more governed by stochastic processes acting on local gas concentrations. Infrared observations provide complementary information by tracing emission from dust grains that are heated by ultraviolet photons from young stars. In NGC 4395, the infrared luminosity associated with star-forming regions is relatively weak compared with that of more massive spirals, indicating a modest dust content and a limited amount of heavily obscured star formation. When combined with ultraviolet measurements, the data suggest that a significant fraction of the young stellar population is visible in the ultraviolet and optical bands, simplifying the task of reconstructing recent star formation histories. The dust present in the disk is sufficient to redden starlight in star-forming complexes and to produce some infrared emission, but not so abundant as to hide large reservoirs of intense embedded activity. Over longer timescales, the cumulative effect of these scattered star-forming events builds up the stellar disk. Studies that model the color distribution of stars across NGC 4395 indicate that star formation has proceeded at a relatively steady low rate over several billion years rather than in a small number of brief intense bursts. The presence of intermediate age populations alongside both young and old stars supports a scenario in which the galaxy has converted its gas into stars gradually. The ongoing star formation seen in current tracers is therefore part of a sustained process that has operated over much of the galaxy's lifetime, regulated by the availability of gas and by the gentle dynamical environment described in earlier sections. In some locations, the feedback from young stars shapes the immediate surroundings. Stellar winds and supernova explosions inject energy into the interstellar medium, creating shells and bubbles in the gas. These structures can be identified as cavities in neutral hydrogen maps, or as ring-like features in ionized gas images. In NGC 4395, such feedback-driven structures are generally small, reflecting the modest scale of the underlying star-forming regions, but they still play a role in redistributing gas and possibly triggering secondary episodes of star formation at their edges. The overall pattern that emerges from these observations is one of a galaxy where many small distributed star-forming regions punctuate a faint extended stellar disk, each contributing a limited amount of new mass, while collectively sustaining the gradual growth of the system over cosmic time. In NGC 4395, the interstellar medium in the disk consists primarily of neutral atomic hydrogen, with smaller contributions from molecular gas and ionized gas, and this mixture extends well beyond the main concentration of starlight. Radio observations at the 21 centimeter line of neutral hydrogen show that the gas disk reaches to radii larger than those traced by the optical surface brightness profile, forming an extended envelope whose column density declines gradually with distance from the center. In the inner regions of the disk, the neutral hydrogen surface density reaches values high enough to support ongoing star formation in localized patches, while in the outer disk the gas becomes more diffuse, and the inferred star formation rate per unit area is very low. The velocity field of the neutral hydrogen mapped through the Doppler shifts of the emission line traces the rotation of the galaxy, and provides one of the main tools for deriving its rotation curve and total mass distribution. In NGC 4395, this velocity field is relatively regular on large scales, indicating that the gas follows approximately circular orbits in a flattened potential, but local deviations from pure rotation are present around star-forming complexes and regions with disturbed kinematics. These deviations can arise from expanding shells driven by stellar feedback from small-scale non-axis emmetric structures in the disk, or from mild tidal influences from neighbouring galaxies. The overall regularity of the velocity field supports the classification of NGC 4395 as a disk system despite its patchy appearance in starlight. Molecular gas, usually traced by carbon monoxide emission, is more difficult to detect in low-mass, low-metallicity galaxies because the lower abundance of heavy elements and dust reduces both the formation and the shielding of molecules. In NGC 4395, measurements of molecular gas are sparse and often result in non-detections or in the identification of only small reservoirs concentrated near active star-forming regions. This suggests that the molecular phase constitutes a relatively small fraction of the total gas mass, although it remains crucial as the immediate fuel for star formation where it is present. The bulk of the interstellar medium by mass appears to be in the form of neutral atomic hydrogen, with the molecular component confined to dense clumps embedded within this broader atomic disk. Ionized gas is present mainly in the form of H2 regions around young stars and in diffuse ionized gas that pervades parts of the disk. The emission lines from this gas provide information about the chemical composition and physical conditions of the interstellar medium. Abundance measurements in H2 regions of NGC 4395 indicate subsolar metallicities consistent with its low mass and dwarf spiral status. Gradients in metallicity with radius appear to be weaker than in some larger spirals, although the limited number of well-measured regions introduces uncertainties. The relatively uniform low metallicity environment affects the cooling properties of the gas and the formation of dust grains. Dust in NGC 4395 is detected through its effects on starlight, such as reddening and extinction, and through infrared emission from heated grains. Optical images show lanes and patches of dust absorption, particularly near star-forming regions and along some arm fragments, but the overall dust content is modest compared with that of more massive metal-rich spirals. Infrared observations reveal emission from warm and cold dust components that trace both recently heated regions near young stars and more diffuse dust mixed with the general interstellar medium. The ratio of infrared to ultraviolet or optical luminosity implies that only a limited fraction of the stellar radiation is absorbed and re-emitted by dust consistent with a relatively transparent disk. The vertical distribution of gas and dust in NGC 4395 is less well constrained than the radial distribution, but by analogy with other late-type dwarfs, and from the broadening of emission lines, the gas layer is expected to have a larger scale height than in high mass spirals. The weaker vertical gravitational field produced by the low stellar surface density and the dark matter halo allows gas to occupy a thicker layer above and below the midplane. This thicker gas layer contributes to the diffuse appearance of the disk and may influence the propagation of feedback-driven outflows from star-forming regions. Turbulent motions within the gas with characteristic velocities of a few to several kilometers per second help support the layer against collapse and are driven by a combination of stellar feedback, gravitational instabilities, and shear. Within the extended atomic disk, there are signatures of warps or asymmetries at large radii. In many low-mass galaxies, the outer gas disk deviates from a single well-defined plane, and NGC 4395 shows hints of such behavior in the form of slight twists in the position angle of the kinematic major axis and in the shape of outer isophotes in the neutral hydrogen maps. These features may reflect the response of the gas to the gravitational potential of the dark matter halo to past minor interactions, or to the ongoing accretion of low-density intergalactic gas. In any case, the presence of an extended, somewhat warped gas disk indicates that the interstellar medium of NGC 4395 is not confined strictly to the region of higher stellar density, but participates in a larger scale structure that connects the optical galaxy to its surrounding environment. Dust mixed with this gas attenuates starlight passing through the disk, but the low overall dust content means that extinction corrections for integrated properties are moderate. For individual star-forming regions, however, local dust concentrations can produce significant variations in observed colors and emission line strengths, which must be accounted for when deriving star formation rates and chemical abundances. The combined gas and dust distribution thus governs both the appearance of NGC 4395 in different wavelength bands and the physical conditions under which stars form and evolve within its extended disk. Comparisons with other low-surface brightness spirals show that NGC 4395 falls near the regime where gas surface densities are close to empirical thresholds for widespread star formation, so small variations in local density, turbulence, or external pressure can determine whether a given patch of gas remains quiescent or forms stars. The stellar populations of NGC 4395 can be examined in unusual detail for a dwarf spiral galaxy, because its relative proximity allows individual stars and small clusters to be resolved across much of the disk. Deep imaging in visible and near-infrared bands separates the brightest stars from the diffuse background of unresolved light and color. Magnitude diagrams constructed from these data provide a record of the galaxy's past star formation. A color magnitude diagram is a plot that shows how bright stars are as a function of their color, which serves as a proxy for surface temperature and, in many cases, age. In NGC 4395, such diagrams reveal the presence of old red giant branch stars, intermediate age asymptotic giant branch stars, and young main sequence stars, indicating that star formation has been ongoing over a large fraction of the galaxy's lifetime. The red giant branch, which consists of evolved low-mass stars that have exhausted hydrogen in their cores, traces a stellar population that is several billion years old. Its prominence in the outer and inner disk demonstrates that NGC 4395 built a substantial part of its stellar mass at early times. The tip of this branch, which corresponds to the brightest red giant stars, has been used as a distance indicator, reinforcing independent estimates of the galaxy's position in the local universe. Above the red giant branch, asymptotic giant branch, stars reveal an intermediate age component with typical ages of a few hundred million to a few billion years. These stars are luminous and relatively cool, contributing significantly to the near-infrared light of the galaxy despite their small numbers. Their presence across the disk implies that star formation did not occur only in a brief primordial episode, but continued at non-negligible rates over extended intervals. Superposed on these older populations is a set of young blue main sequence stars and blue helium-burning stars concentrated near the star-forming regions described in earlier sections. These stars are massive and short, lived with ages of at most a few tens of millions of years, and dominate the ultraviolet and blue optical light in their local environments. Their spatial distribution traces the current pattern of star formation and highlights the association between gas density peaks and recent activity. When the relative numbers of stars in different evolutionary phases are modelled using stellar population synthesis techniques, the inferred star formation history of NGC 4395 is one of gradual fluctuating activity, rather than one dominated by a few strong bursts. The central regions of the disk show a somewhat higher concentration of intermediate age and young stars, while the outer disk is richer in old red giant branch stars and shows fewer very young objects. This radial gradient is consistent with a scenario in which gas has been consumed more efficiently in the inner disk, maintaining star formation there for longer periods, while the outer disk has experienced lower, more sporadic activity. The integrated colours of NGC 4395, when corrected for modest internal extinction, place it among late-type galaxies with ongoing star formation and relatively low metallicity. The low metallicity inferred from both stellar and nebula diagnostics indicates that the overall chemical enrichment of the galaxy has been limited by its low mass and by the potential loss of metal-enriched gas through galactic winds. Old stellar populations are not confined to the thin disk alone. In many late-type dwarfs, a thicker component of old stars extends above and below the main plane, forming a low-surface brightness stellar envelope that may represent a rudimentary stellar halo or thick disk. In NGC 4395, star counts along lines of sight that pass above the main disk plane reveal an excess of old red stars relative to what would be expected from a single thin disk alone. This suggests the existence of a thicker distribution of ancient stars, although the exact geometry and mass fraction of this component remain uncertain due to the low surface brightness. If present, such a thick component provides evidence that part of the stellar population formed early under different dynamical conditions, or was heated vertically by subsequent processes such as minor interactions, spiral structure, or feedback-driven turbulence. Small star clusters in NGC 4395 provide additional constraints on its stellar content. High-resolution images show numerous compact groups of stars with sizes of a few parsecs and luminosities ranging from those of modest open clusters to those approaching the lower end of the mass range for classical star clusters in larger galaxies. Photometric analysis of these clusters indicates a range of ages. Some are young, associated with current or recent star-forming regions, and dominated by blue main sequence stars. Others show redder colours consistent with intermediate or old ages, suggesting that they formed several 100 million years to several billion years ago, and have survived the disruptive influences of tidal forces and internal dynamics. The mass function of clusters in NGC 4395 appears to be weighted toward low and intermediate masses with relatively few very massive dense clusters. This distribution matches expectations for a galaxy with modest gas surface densities and a quiescent interaction history, where the conditions required to form extremely massive clusters are rare. The spatial distribution of clusters mirrors to first order the distribution of star-forming regions in the underlying stellar disk. Young clusters are concentrated in and near the sites of active star formation, while older clusters are more widely dispersed, sampling a broader range of radii and azimuths. This pattern reflects both the migration of clusters over time and the long-term evolution of the sites at which they formed. Some clusters may have been disrupted by tidal forces within the disk or by encounters with massive gas clouds, contributing their stars to the diffuse field population. Others remain intact and serve as long-lived traces of past episodes of star formation. The combination of resolved stellar populations and cluster photometry allows detailed modelling of the global star formation rate as a function of time. Studies that fit synthetic colour magnitude diagrams to the observed ones, taking into account observational completeness and photometric uncertainties, generally find that NGC 4395 has maintained a low but relatively steady star formation rate over the past several billion years, with fluctuations on shorter timescales, but no evidence for long periods of complete quiescence. This continuous activity has gradually built up the stellar mass of the galaxy, while preserving its low surface brightness and late-type morphology. The presence of an extended old population intermediate age stars and ongoing formation of young stars and clusters shows that NGC 4395 hosts a multi-component stellar system whose properties are shaped by its low mass, its gas-rich disk, and its relatively undisturbed environment in the nearby universe. In NGC 4395, the interstellar structure continues the pattern seen in the outer disk, rather than transitioning into a dense spheroidal bulge, and this absence of a classical bulge is one of the key structural features of the galaxy. In many spiral galaxies, the surface brightness profile in the central regions shows a steep upturn relative to the outer exponential disk, and this excess light is attributed to a bulge component that contains a high density of old stars, with random motions in 3 dimensions. In NGC 4395, photometric decompositions of the light profile can be described adequately by an exponential disk, plus a compact nuclear component without the need for a massive extended bulge. The central surface brightness is only moderately higher than the inner disk, and the radial profile does not exhibit the strong rounder component characteristic of a classical bulge, with a steep Circic profile, where a Circic profile is a mathematical function used to describe how surface brightness changes with radius in galaxies. Measurements of isophotral shapes near the centre support this conclusion. Instead of transitioning from flattened disk-like isophotes to rounder ones dominated by a spheroidal bulge, the contours in NGC 4395 remain flattened and aligned with the disk out to small radii. Any central excess above the exponential disk is confined to a very compact region, associated with the nucleus rather than an extended kiloparsec scale structure. This behavior, together with the low total luminosity of the galaxy, leads to its classification as a bulgeless or nearly bulgeless spiral. Kinematic studies provide additional evidence for the lack of a classical bulge. In a typical bulge-dominated central region, stellar motions show high-velocity dispersion and relatively low-ordered rotation, reflecting a pressure-supported system. In contrast, observations of the inner regions of NGC 4395 indicate that ordered rotation remains the dominant kinematic feature, and that the velocity dispersion of the stars does not rise to values expected for a substantial bulge. Gas kinematics show a similar pattern, with the rotation field continuing inward without a dramatic change that would signal a transition to a massive spheroidal component. The combination of a disk-like light distribution and rotation-dominated kinematics supports a picture in which the interstellar structure is essentially an extension of the disk with only minor modifications. In some late-type spirals, central light concentrations that are more flattened and rotation-supported are classified as pseudo-bulges, where a pseudobulge is a central light concentration built gradually from disk material, rather than in an early violent event. These structures are thought to arise from secular evolution, meaning slow internal processes within the disk, rather than from major mergers. In NGC 4395, any such pseudo-bulge must be extremely small or absent, because the central excess light is limited and strongly concentrated around the nuclear star cluster and active core. Structure decompositions that include a pseudobulge component generally find that its contribution to the total luminosity is minor compared with the disk. The lack of a significant bulge in NGC 4395 has implications for how the galaxy fits into empirical scaling relations that link global structure to formation history. In more massive systems, the presence of prominent bulges is often associated with complex assembly histories involving mergers and early collapse, while pure disk or bulgeless galaxies are thought to have experienced quieter, more secular evolution with fewer disruptive events. The location of NGC 4395 in a low-density environment and the apparent regularity of its extended gas disk are consistent with a history that has avoided major mergers capable of building a dense classical bulge. Instead, gradual gas accretion and internal instabilities within the disk are likely to have played the dominant roles in shaping its structure. The absence of a bulge also affects the vertical structure of the inner regions. In bulge-dominated spirals, the central stellar density peaks strongly toward the midplane and then declines with height on short-scale lengths. In NGC 4395, the central vertical profile inferred from star counts suggests a thicker distribution that does not reach the high central densities of a classical bulge. Old stars are present in the inner disk as indicated by red giant branch and asymptotic giant branch populations, but their spatial distribution remains broadly consistent with a disk or thick disk geometry, rather than a centrally concentrated spheroid. The thin and thick disk components together provide the main reservoir of old stars throughout the galaxy, including the inner radii. Embedded within this disk, dominated context is a compact nuclear region whose stellar light is superposed on the inner disk, but does not extend far enough or carry enough mass to qualify as a classical bulge. High-resolution imaging reveals a nuclear star cluster with a size of only a few parsecs and a luminosity that, while significant, remains small compared with the total light of the galaxy. This cluster coexists with the active nucleus and contributes to the central point-like or slightly extended source seen in high-quality images. However, the nuclear cluster is a distinct structural component different from a kiloparsec scale bulge both in size and in dynamical role. Its presence demonstrates that central mass concentrations can form in disk galaxies through localized processes without building a full bulge. Beyond the nucleus, the stellar density declines smoothly into the inner disk without a sharp break. This continuity reinforces the interpretation of NGC 4395 as a galaxy whose inner stellar structure is essentially disk-like all the way into very small radii. Photometric studies that compare NGC 4395 with samples of bulgulous and bulge-dominated spirals place it among the former, both in terms of its light profile and its morphology. Multi-wavelength imaging from optical to near-infrared bands yields consistent decompositions with no evidence for a hidden dust-reddened bulge component. At all these wavelengths, the central light remains dominated by the disk and the compact nuclear cluster. Comparisons with statistical samples show that galaxies with similar low mass and rotation speeds also frequently lack classical bulges, placing NGC 4395 within a broader class of disk-dominated systems in the local universe. Taken together, these structural measurements indicate that NGC 4395 is a bulgeless spiral galaxy in the nearby universe with a low surface brightness disk that extends inward to the smallest resolved radii and a central region dominated by a compact nuclear star cluster, an active core rather than by a massive stellar spheroid. In NGC 4395, there is a gradual transition from the low surface brightness stellar disk into a more crowded central region, where gas stars and the active nucleus interact on smaller spatial scales. This inner zone occupies a region of a few hundred to perhaps around 1,000 light-years in radius, where the surface density of stars and gas increases relative to the outer disk, and where structural features that are not conspicuous at larger radii become more prominent. Optical and near-infrared images resolve this area into a mixture of compact star clusters, diffuse stellar light, and patches of dust and ionized gas. The overall geometry remains that of a flattened disk, but the concentration of material toward the center produces a central light enhancement that stands out against the exponential decline of the outer disk. Unlike galaxies with a strong bulge, however, the central enhancement in NGC 4395 does not correspond to a massive spheroidal component. Instead, it reflects the combined contributions of the inner disk, the nuclear star cluster, and the unresolved light from the active nucleus. The line of sight through this region passes through multiple structural elements, including spiral arm fragments that curve inward gas lanes that trace the paths of inflowing material and small associations of young stars. High-resolution imaging reveals that the central few hundred light-years contains several distinct clusters with sizes of a few parsecs and luminosities comparable to intermediate-mass young clusters elsewhere in the disk. Some of these clusters are associated with ongoing or recent star formation, as indicated by the presence of nearby ionized gas and blue main sequence stars, while others are older, and contribute primarily to the red and near-infrared light. Their spatial distribution is not perfectly symmetric. Instead, clusters and associations are arranged in a somewhat irregular pattern around the center, reflecting the stochastic nature of star formation and gas inflow in a low-mass disk. Superposed on this configuration is a compact nuclear star cluster, whose half-light radius is only a few parsecs, and whose luminosity makes it the single most prominent stellar structure in the very center. Spectroscopic observations show that this cluster contains a mixture of stellar populations with different ages, implying that star formation there has occurred in multiple episodes over time. The nuclear cluster is embedded in ionized gas and is coincident with the active nucleus, so its light is blended with emission from the accretion-powered source in many observations. Separating the contributions of the cluster and the active core requires careful modelling of the point spread function and the spectral energy distribution, but the presence of both components is a robust result. Gas in the central region of NGC 4395 shows complex kinematics. While the large-scale velocity field of the disk is dominated by ordered rotation, the inner few hundred light-years exhibit deviations from simple circular motion. Emission lines from ionized gas display line widths and velocity shifts that vary with position, indicating the presence of local flows turbulence and possible inflows or outflows. Some of these motions are likely connected to the influence of the active nucleus, which can drive ionized gas outflows along preferred directions, while others may be associated with the gravitational potential of the nuclear star cluster and with the dynamical effects of non-axis symmetric structures in the inner disk. The absence of a strong, well-defined bar does not preclude the existence of weaker oval distortions or spiral features that can exert torques on the gas and promote radial transport. In such a setting, gas can gradually lose angular momentum and drift inward from kiloparsec scales to the central few hundred parsecs accumulating in the vicinity of the nucleus. Observations of emission line ratios in the central region indicate a mixture of ionization sources. In some locations, line ratios characteristic of H2 regions show that young stars dominate the ionization, while closer to the nucleus, the line ratios transition to those typical of an active galactic nucleus. This spatial variation reflects the superposition of star-forming regions and the narrow line region of the active core within the same central zone. The narrow line region is the region of ionized gas that extends over tens to hundreds of parsecs around the active nucleus and is photoionized by its radiation. In NGC 4395, the narrow line region appears relatively compact compared with those in more luminous Seyfert galaxies, consistent with the lower luminosity of the central source and the small scale of the host galaxy. Dust structures in the inner region, visible as lanes and patches of extinction against the stellar background, follow paths that are often aligned with spiral features and gas lanes. These dust concentrations mark the locations of denser, cooler gas that has not yet formed stars or that is in the process of doing so. The distribution of dust is clumpy rather than smooth, and its covering fraction is modest, so that the central regions are only partially obscured. Nevertheless, the presence of dust affects the observed colours of stars and the apparent brightness of the nucleus, requiring extinction corrections when deriving intrinsic luminosities. Infrared observations help to compensate for this by probing through some of the dust and by detecting emission from warm dust heated by both young stars and the active nucleus. The gravitational potential in the transition zone between the disk and the central region is shaped by the combined mass of the stellar disk, the nuclear star cluster, the gas and the dark matter halo. Rotation curve measurements indicate that the circular velocity continues to rise slowly, or remains roughly flat as one approaches the inner radii without the sharp peak that would be expected if a very massive bulge were present. This behaviour suggests that the inner mass distribution is relatively shallow, with no dominant central stellar spheroid. Instead, the mass is distributed among the extended disk and the compact nuclear components. Dynamical estimates of the nuclear star cluster mass based on its luminosity and stellar population models show that it is massive enough to influence the motions of stars and gas in its immediate surroundings, but it remains much less massive than the dark matter halo and the total stellar disk. The supermassive or intermediate mass black hole, inferred to reside at the exact centre, adds an additional point-like contribution to the potential that becomes significant only on very small scales far inside the resolution of most current imaging. As gas and stars move through this transition region, their orbits and interactions set the conditions for how material is supplied to the active nucleus, and how the nucleus in turn can affect its surroundings. The central few hundred light-years of NGC 4395 are therefore characterized by an interplay between disk-like structure, compact star clusters, clumpy gas and dust, and the influence of the active core, all within a framework that remains dominated by the general disk geometry rather than by a classical bulge. The immediate surroundings of the active nucleus in NGC 4395 occupy a region in which the structural simplicity of the disk and the absence of a classical bulge intersect with the complex physics of ionized gas and compact stellar systems. On scales of a few tens of light-years to a few hundred light-years, stars, gas and dust form a circumnuclear zone that mediates the interaction between the small central engine and the larger galactic disk. High-resolution imaging resolves this area into a compact nuclear star cluster, neighbouring stellar associations, patches of ionized gas and small dust lanes, all embedded within the inner disk. The nuclear star cluster sits at the photometric centre of the galaxy and coincides within observational uncertainties with the dynamical centre indicated by gas and stellar kinematics. Its stellar light dominates the resolved emission within a radius of a few parsecs, although the total luminosity is still modest compared with the entire galaxy. Spectroscopic studies show that the cluster contains multiple stellar populations, with evidence for both old stars and younger components that formed in episodes separated by hundreds of millions of years. This mixture implies repeated inflow of gas into the central region over long timescales sufficient to power intermittent star formation, in addition to the accretion activity associated with the black hole. the stellar mass of the cluster is large enough to influence the gravitational potential, locally shaping the orbits of stars and gas in its vicinity, but it remains small compared with the dark matter halo and the global stellar disk. Surrounding the nuclear cluster is a distribution of ionized gas that forms the narrow line region of the active nucleus. The narrow line region is a zone of low-density ionized gas extending over tens to perhaps a few hundred light-years, photoionized by the radiation from the central source and emitting characteristic narrow emission lines in the optical and ultraviolet. In NGC 4395, this region is compact compared with those in more luminous Seyfert galaxies, reflecting both the low luminosity of the nucleus and the small scale of the host galaxy. Imaging and spectroscopy and strong emission lines, such as those from doubly ionized oxygen and hydrogen recombination, reveal clumpy and filamentary structures rather than a smooth symmetric shell. The gas density inferred from diagnostic line ratios lies in a range typical for narrow line regions with electron densities of a few hundred to a few thousand particles per cubic centimeter, in the brighter knots decreasing further out. Ionization-sensitive line ratios show a gradient with distance from the center, with higher ionization states favored closer in, and lower ionization lines becoming relatively stronger at larger radii, consistent with a central source of ionizing photons whose radiation field hardens or softens with distance. Kinematically, the ionized gas in the surroundings of the nucleus exhibits both ordered and disordered components. The large-scale rotational pattern of the disk can still be traced inward, but near the nucleus the emission line profiles broaden and show asymmetries. These features indicate local motions that deviate from pure circular rotation. Some velocity components are shifted in a way that suggests mild outflows where gas is pushed outward by the combined effects of radiation pressure, gas pressure, and possibly weak jets from the active nucleus. Other components may trace inflows in which gas loses angular momentum and moves inward along spiral paths or through irregular gravitational torques. The small physical scale of the region and the limited spatial resolution of available data make it challenging to separate these processes cleanly, but the overall pattern is one of a dynamically active environment in which gas is both supplied to and in part expelled from the immediate surroundings of the black hole. The distribution of star formation in the circumnuclear region is patchy. Some compact H2 regions and young stellar clusters lie within a few hundred light-years of the nucleus, indicating that star formation can proceed even in the presence of the active core. Emission line diagnostics in these zones show line ratios characteristic of photoionization by young stars rather than by the hard radiation field of the nucleus. Spatially resolved spectroscopy reveals a transition from star formation-dominated excitation to active nucleus-dominated excitation over distances of tens to a few hundred light-years. This coexistence of star-forming regions and the narrow line region is important because it complicates the interpretation of integrated spectra and requires careful separation of contributions when deriving physical parameters such as metallicity, ionization parameter, and star formation rate in the central zone. Dust in the surroundings of the nucleus is arranged in small lanes and patches that intersect the line of sight to parts of the nuclear region. These dust structures trace cold gas reservoirs that are potential future fuel for both star formation and accretion. In optical images, they appear as irregular dark features against the stellar background, often aligned with inner spiral features or gas lanes that curve toward the center. Infrared observations detect emission from warm dust grains heated by the ultraviolet and optical radiation from both the active nucleus and nearby young stars. The total dust mass inferred from these observations is modest, but the concentration of dust close to the nucleus can still exert a significant influence on the local radiation field and on the appearance of the central source. Patchy obscuration by circumnuclear dust may cause anisotropies in the observed emission lines, and continuum and small variations in column density along different lines of sight can lead to differences in observed spectral properties. On scales just outside the narrow line region, the gas is predominantly neutral or weakly ionized and forms part of the inner atomic and molecular disk. Here the gas density and pressure are higher than in the outer disk, and the dynamical timescales are shorter, so this region acts as a reservoir from which material can be drawn inward. The inner gas disk shows subtle non-axis symmetric features such as slight twists in the kinematic major axis, and mild elongations in projected density, which may be signatures of weak oval distortions or inner spiral modes in the gravitational potential. These features can exert torques on the gas, allowing gradual angular momentum transfer that supports slow inflow toward the nucleus without the need for a strong bar. The interplay between the nuclear star cluster, the narrow line region, circumnuclear star-forming zones, and the inner gas disk defines the local environment in which the central black hole in NGC 4395 resides. Each component contributes to the physical conditions experienced by gas as it moves inward, including its density, temperature, chemical composition, and exposure to radiation. At the same time, radiation and mechanical energy from the active nucleus and from young stars feed back into the surroundings, heating, ionizing, and stirring the gas. The result is a multi-phase medium in the central few hundred light-years that is neither extremely dense nor extremely energetic by the standards of luminous active galaxies, but is nevertheless sufficiently structured and dynamic to support ongoing low-level accretion and star formation in close proximity to a low-mass active nucleus in a bulgeless dwarf spiral host. The active nucleus of NGC 4395 is classified as a Seyfert Type 1 nucleus, meaning that it resides in a disk galaxy and displays strong emission lines and a bright continuum source powered by accretion onto a central black hole with both broad and narrow permitted emission lines visible in its optical spectrum. In general, an active galactic nucleus is defined as a compact region at the center of a galaxy where gravitational energy released by gas falling inward is converted into radiation over a wide range of wavelengths from radio to X-rays. In NGC 4395, this region is unusually faint in absolute terms compared with classical Seyfert galaxies, yet its luminosity is high relative to the low-mass, low-surface brightness host. Optical spectroscopy of the nucleus reveals a continuum that rises towards shorter wavelengths in the blue and ultraviolet superposed with a set of emission lines from hydrogen, helium, and heavier elements in various ionization states. The permitted hydrogen lines, such as those in the Balmer series, show profiles with broad wings extending over several thousands of kilometers per second in velocity space, along with narrower cores only a few hundreds of kilometers per second wide. The broad components originate in fast-moving gas located close to the central object, while the narrow components are produced by lower velocity gas at larger radii. The simultaneous presence of both components in the same permitted lines is the defining signature of a Type 1 Seyfert nucleus. The forbidden lines, such as those of doubly ionized oxygen, appear only in narrow form because the densities in the broader inner gas are too high for these lines to be produced efficiently. Diagnostic diagrams that plot ratios of strong emission lines against each other place the nucleus of NGC 4395 firmly in the region associated with active galactic nuclei, rather than H2 regions powered by young stars. These line ratios require a radiation field that is harder and more intense in high-energy photons than that produced by stellar populations alone. The relative strengths of high ionization lines and low ionization lines indicate that gas in the narrow line region is exposed to a continuum extending from the ultraviolet into the X-ray regime. This interpretation is supported by direct X-ray observations which detect a compact variable X-ray source coincident with the optical nucleus. The X-ray spectrum is well described by a power law distribution of photon energies often seen in active galactic nuclei, with additional features produced by absorption and reflection in surrounding gas. The luminosity of the nucleus across all bands is low compared with that of typical Seyfert galaxies, hosted by massive spirals, but it is still high enough that the energy output from accretion dominates over any contribution from young stars within the central few parsecs. Multi-wavelength observations show that the nucleus emits detectable radiation in radio-optical ultraviolet and X-ray bands. In radio frequencies, a compact core is present with a flat or slightly inverted spectrum indicating non-thermal emission that may originate in a weak jet or in the immediate surroundings of the accretion flow. The radio luminosity is modest, and there is no evidence for large-scale radio jets or lobes, so the nucleus is classified as radio quiet. In the optical and ultraviolet, the continuum emission is associated with the accretion disk and its immediate environment, while the emission lines arise from gas clouds ionized by this continuum. In X-rays, a combination of primary emission from a hot compact corona and reprocessing in surrounding gas produces a variable spectrum that carries information about the innermost regions of the active nucleus. The overall spectral energy distribution of the nucleus when plotted as energy output per unit frequency, or wavelength, follows the general form seen in other low-luminosity active galactic nuclei, with a broad peak in the optical and ultraviolet, and a non-thermal tail in X-rays. The relative weakness of the ultraviolet component compared with some more luminous Seyfert nuclei has led to its classification as a low-luminosity system that accretes at a small fraction of the Eddington limit, where the Eddington limit is the theoretical luminosity at which radiation pressure balances gravity for spherical accretion. Detailed modelling of the spectrum indicates that the rate at which mass is supplied to the central engine is low in absolute terms, but high enough given the comparatively small black hole mass inferred from other measurements to produce the observed luminosities. One of the notable properties of the active nucleus in NGC 4395 is its strong variability. Optical and X-ray observations show changes in flux on timescales ranging from hours to days and longer. The amplitude of these variations can be large, with fluxes changing by factors of several over short intervals. The rapidity of the variability implies that much of the emission arises from a very compact region, because the timescale over which the flux can change is limited by the light travel time across the emitting zone. For NGC 4395, the short variability timescales point to an emitting region comparable in size to the expected inner accretion flow around a low-mass black hole. In addition, changes in the continuum flux are accompanied by responses in the broad emission lines, with time delays that reflect the light travel time between the continuum source and the broad-line gas. Measurements of these delays through reverberation mapping techniques have been used to estimate the characteristic size of the broad-line region, and in combination with the widths of the broad lines to infer the mass of the central black hole. While the precise mass estimates will be discussed in later sections, the existence of a measurable time lag and broad-line response confirms that the nucleus of NGC 4395 functions as a scaled-down version of more luminous Seyfert nuclei with similar physical structures operating at lower luminosity and smaller spatial scales. The classification of NGC 4395 as a Seyfert Type 1 nucleus hosted by a dwarf bulgeless spiral galaxy makes it an important reference object for studies of active galactic nuclei at the low-mass, low-luminosity end of the population. Its emission line spectrum variability properties and multi-wavelength output demonstrate that the standard active nucleus components, namely a compact continuum source, a broad line region, and a narrow line region, can all be present in a system whose host galaxy has a very low stellar mass and no classical bulge. The nucleus thus provides a case in which the physics of gas accretion onto a central black hole can be examined under conditions that differ significantly from those in the massive bulge-dominated galaxies that host many well-studied Seyfert nuclei. The accretion flow in NGC 4395 occupies the innermost region around the central black hole, extending from the immediate vicinity of the event horizon out through the broad line region and into the zones of ionized and partially ionized gas that imprint absorption features on the X-ray spectrum. Direct imaging of this region is not possible with current instruments, so its structure is inferred from timing and spectral analyses across multiple wavebands. In broad outline, the nucleus appears to host the same basic components seen in more luminous Seyfert galaxies, scaled down in size and luminosity to match the low mass of the central black hole and the modest gas supply in the host galaxy. The accretion flow is thought to include an optically thick, geometrically thin accretion disk that extends from an inner radius of a few gravitational radii out to much larger distances, together with a compact region of hot electrons often referred to as a corona that produces the primary X-ray continuum through inverse Compton scattering of lower energy photons. Evidence for a disk-like structure comes from the shape of the optical and ultraviolet continuum, and from variability studies that suggest a stratified emitting region in which shorter wavelength emission responds more rapidly to changes in the central source than longer wavelength emission. X-ray spectra and their changes with time provide the main constraints on the inner gas structures. In NGC 4395, careful analysis of long observations has revealed that the soft X-ray emission is strongly affected by absorption in ionized gas, along the line of sight often described as a warm absorber. The spectrum requires more than one zone of ionized gas to explain the detailed shape of the absorption, indicating a multi-zone warm absorber with different ionization parameters and column densities at different radii. In addition, there is evidence for a separate layer of colder, less ionized gas that partially covers the source, producing variations in the observed spectrum as different parts of the emission region are obscured or revealed. This picture of multiple absorbing layers, some ionized and some cold, is consistent with a clumpy circumnuclear environment in which gas clouds at different distances from the black hole intercept the radiation from the accretion flow. The warm absorber in NGC 4395 responds to changes in the continuum flux, with the depth and shape of absorption features evolving as the ionization state of the gas adjusts to the varying radiation field. This behavior shows that the absorber lies at a distance where ionization and recombination timescales are comparable to observed variability, timescales placing it within a range of distances that likely overlaps or lies just outside the broad line region. The need for multiple ionization zones suggests a stratified structure in which denser, less ionized gas resides closer to the midplane, or in denser clumps, while more highly ionized lower density gas occupies a more extended volume. Some components may be outflowing as indicated by modest blue shifts in absorption lines, while others may be nearly stationary in the galaxy frame. The cold partially covering absorber inferred from changes in the X-ray spectrum appears and disappears on timescales of hours to days, implying that individual clouds or filaments cross the line of sight on correspondingly short timescales. The velocities required for such transits at plausible distances from the center are consistent with those expected for clouds in the broad line region or in its immediate surroundings. In this scenario, variability in the soft X-ray band is driven not only by intrinsic luminosity changes in the accretion flow, but also by changes in the covering fraction and column density of the intervening material. The geometry may resemble a distribution of dense clouds, embedded in a more diffuse warm medium with both components illuminated by the central continuum source. The broad line region itself is part of the accretion flow environment. It consists of high-velocity gas clouds at distances of light hours to light days from the central source moving in the gravitational potential of the black hole. In NGC 4395, reverberation mapping of the broad emission lines indicates that this region is extremely compact compared with those in typical Seyfert galaxies, as expected for a central mass that is orders of magnitude smaller. The line widths and response times imply that the broad line gas orbits at velocities of thousands of kilometers per second at radii of only a few light hours to a small fraction of a light day. Although the broad line region is traditionally treated as distinct from the accretion disk, it can be viewed as one part of the broader accretion structure representing gas that is lifted off the disk in a disordered cloud-like distribution, while still bound to the central potential. Outside the broad line region, the warm absorber and partially covering cold gas represent further stages in the interaction between the accretion flow and the surrounding interstellar medium. The inflow of gas from the inner disk into the accretion structure must cross these regions, and the radiation and possible outflows from the inner accretion flow feed back on them. X-ray spectra of NGC 4395 show not only absorption, but also a narrow ion emission line at an energy corresponding to neutral or low ionization ion. This line is attributed to reflection of hard X-rays by relatively cold material at larger radii, possibly in the outer accretion disk or in distant circumnuclear gas. The presence of this line indicates that a fraction of the primary X-ray emission is intercepted and re-emitted by material that subtends a significant solid angle, as seen from the central source. The line is narrow, which suggests that the reflecting material is located far enough from the black hole that relativistic broadening is modest, consistent with scales of many gravitational radii or larger. Closer in there is evidence from some observations for a broader ion line component that could arise from the inner regions of the accretion disk, where strong gravity and rapid rotation distort the line profile. Interpreting this broader component requires careful modelling of the continuum and absorption, and in NGC 4395 the low signal and complex absorption make the exact strength and shape of any relativistic line uncertain. Nevertheless, the possible presence of such a feature supports the idea that the accretion disk in this galaxy extends inward to radii, where relativistic effects become important. The energy dissipated in the accretion flow emerges partly as optical and ultraviolet emission from the disk and partly as X-rays from the corona. The relative strengths of these components, together with the level of reflection and absorption, define the spectrum that illuminates the surrounding gas. In NGC 4395, the low total luminosity means that the ionizing flux is modest, compared with that in luminous Seyfert galaxies, but the compactness of the emitting region and the proximity of the absorbing gas ensure that ionization parameters remain in ranges typical of warm absorbers. The multi-zone structure allows some gas to remain only mildly ionized, while other gas is driven to higher ionization states, leading to a complex blend of absorption features in the observed spectrum. Taken together, the accretion flow and inner gas structures in NGC 4395 form a scaled-down but otherwise recognizable version of the accretion environments seen in more massive active galactic nuclei with a thin disk, and hot corona feeding a low-mass black hole surrounded by a compact broadline region, stratified warm absorbers, and partially covering cold gas that collectively shape the emergent radiation field and its variations. The emission from the active nucleus in NGC 4395 varies strongly across several wavelength bands, and these variations provide one of the most direct probes of the size and structure of the innermost regions around the central black hole. In the X-ray band, observations show rapid changes in flux on timescales, as short as a few hundred seconds to a few hours, with longer-term trends extending over days and weeks. The amplitude of these variations can reach factors of several in flux over relatively short intervals, indicating that the emitting region is compact, because the characteristic variability timescale cannot be much shorter than the light travel time across the source. For a central engine of low mass, such rapid variability is expected, and the timing properties in NGC 4395 fall in line with this expectation. Power spectral density analyses of X-ray light curves which quantify how the variability power is distributed over different temporal frequencies show a steep decline in power at high frequencies and a flattening at low frequencies with a characteristic break frequency that is higher than in more massive Seyfert galaxies. Empirical scaling relations between this break frequency, black hole mass, and accretion rate derived from samples of active nuclei and stellar mass black holes place NGC 4395 at the low mass low luminosity end of the sequence. The presence of a measurable break in the power spectrum supports the view that the variability is generated by processes in the accretion flow that operate over a range of radii and timescales, such as fluctuations in the mass accretion rate that propagate inward. In addition to changes in X-ray flux, NGC 4395 exhibits spectral variability. As the overall brightness changes, the relative contributions of different spectral components shift. In some epochs, the spectrum appears harder, meaning that higher energy photons become more prominent relative to lower energy ones, while in other epochs the spectrum becomes softer. These changes can be produced by a combination of intrinsic variations in the corona that generates the primary X-rays and changes in the absorption along the line of sight due to the warm and cold gas described previously. Time-resolved spectroscopy shows that both effects are at work. The underlying continuum steepens or flattens, and the depths of absorption features and overall attenuation vary as absorbing gas responds to or moves across the line of sight. This interplay leads to complex patterns in which flux and spectral shape are correlated in some intervals and decoupled in others. The warm absorber responds to changes in the ionizing continuum with delays set by ionization and recombination timescales, so its imprint on the spectrum evolves over time. The partially covering cold absorber can change abruptly when a cloud crosses the line of sight, causing sudden drops or recoveries in soft X-ray flux, without a corresponding intrinsic change in the central source. In the optical and ultraviolet, the continuum emission from the active nucleus also varies, though, on somewhat longer characteristic timescales than the fastest X-ray changes. Monitoring campaigns that follow the optical continuum and broad emission lines over many nights show that the optical flux can change by significant amounts over days to weeks. These variations correlate with time delays with those seen in the broad Balmer emission lines. When the continuum brightens, the line fluxes increase after a lag corresponding to the light travel time from the continuum source to the broadline gas. Measuring these lags as a function of emission line and monitoring their response provides reverberation mapping constraints on the size of the broadline region. In NGC 4395, the lags are very short of order hours to less than a few days, consistent with a compact broadline region, expected for a low-mass central black hole. The correlation between continuum and line variability confirms that the broadline gas is photoionized by the active nucleus and responds in a predictable way to changes in its output. At longer wavelengths in the near-infrared variability studies of NGC 4395 are more limited in part because the contribution from the host galaxy's stars becomes larger relative to the active nucleus, and in part because the nucleus is intrinsically faint. Nevertheless, where sufficient data exist, there is evidence for modest infrared variability that likely tracks changes in the heating of circumnuclear dust and in the emission from the accretion flow. The amplitude of infrared variations is smaller than in the optical and X-rays as expected, if the infrared emission arises in part from dust at larger radii that responds more slowly to changes in the central source. Any time lags between optical and infrared variations in this system are expected to be short, reflecting the small physical scale of the circumnuclear dust distribution in a dwarf spiral host. In the radio band, the nucleus shows a compact low-luminosity source whose variability is less well constrained due to the difficulty of frequent high-sensitivity monitoring, but available measurements suggest that any changes are smaller in amplitude and slower than those at higher energies. This pattern, in which the strongest, fastest variability appears in X-rays, with progressively weaker and slower variability at optical and infrared wavelengths, matches the general picture in which the innermost regions of the accretion flow emit the highest energy photons and respond most rapidly to changes in accretion conditions, while larger scale structures such as the broadline region, circumnuclear dust and extended gas respond on longer timescales that reflect their greater distances from the central object. Cross-correlation analyses between light curves in different bands provide further insight into the structure of the emitting regions. In NGC 4395, comparisons between X-ray and optical variations show that changes in the X-ray flux often precede corresponding changes in the optical continuum by short time delays, consistent with a scenario in which a portion of the optical emission is produced by reprocessing of X-ray photons in the accretion disk or a nearby gas. The exact values of these delays and their dependence on photon energy are still subject to measurement uncertainties because of the faintness of the source and the need for dense sampling, but the general pattern supports a model in which the X-ray emitting corona lies close to the black hole and illuminates surrounding material. The variability characteristics also have implications for the accretion rate. The combination of low overall luminosity and strong fractional variability suggests a low accretion rate in absolute terms, with fluctuations that represent significant fractional changes in the local mass inflow. In systems accreting at high fractions of the Eddington limit, the inner disk and corona can be stabilized by radiation pressure and high densities, leading to different variability patterns. In NGC 4395, the low inferred accretion rate relative to the Eddington limit and the strong rapid fluctuations are consistent with a radiatively efficient but low-rate accretion flow, in which local instabilities and turbulence can change the energy release on short timescales. The presence of coherent patterns in the variability across bands indicates that despite the low mass and luminosity, the accretion flow and its associated emitting regions are coupled in a way that resembles more luminous Seyfert galaxies. Finally, the observed variability places constraints on the geometry and orientation of the nucleus. The detection of broad emission lines and strong X-ray variability indicates that the central continuum source and broadline region are not completely obscured along our line of sight, implying a relatively low inclination view of the inner structure within the framework of unified models of active galactic nuclei. At the same time, the presence of variable partial covering absorption shows that there are clumps of gas and dust intersecting the line of sight at small radii. The coexistence of these features suggests a circumnuclear environment with an inhomogeneous, possibly flattened distribution of gas and dust that only partially intercepts the radiation from the compact central engine. The multi-wavelength variability of NGC 4395 thus encodes information about the sizes, locations, and physical states of the components of its accretion environment, and demonstrates that the same physical mechanisms responsible for variability in more massive active galactic nuclei operate in a scaled form in this low-mass, low-luminosity system. The central black hole in NGC 4395 is identified through a combination of spectral signatures, variability and dynamical constraints that together indicate the presence of a compact mass concentration with a mass in the regime between typical stellar mass black holes and the much larger black holes found in massive galaxies. The primary evidence comes from the properties of the active nucleus described in earlier sections. The presence of broad permitted emission lines with widths of several thousands of kilometers per second implies gas moving at high velocities in a deep gravitational potential, well very close to the center. Under the assumption that this gas is bound and its motions are dominated by gravity, the line widths and the characteristic radius of the broadline region provide an estimate of the central mass. Reverberation mapping measurements in which time delays between variations in the continuum and in the broad emission lines are used to infer the size of the broadline region yield radii of order light hours to less than a light day. Combining these radii with the observed line widths via the virial theorem produces black hole mass estimates, typically in the range of around 10,000 to several 100,000 times the mass of the Sun. Different reverberation campaigns, analysis, methods and assumptions about the geometry and kinematics of the broadline region give values that do not coincide exactly, but they consistently place the mass well above that of a single massive star and well below that of the central black holes in luminous Seyfert galaxies and quasars. Additional independent constraints come from variability-based scaling relations. The characteristic timescales of X-ray variability, such as the break frequency and the power spectral density, correlate empirically with black hole mass and accretion rate across samples of active galactic nuclei and stellar mass black holes. In NGC 4395, the observed break frequency is higher than in more massive Seyfert nuclei, which corresponds to shorter characteristic timescales, and in these scaling relations to a lower central mass. When these relations are calibrated using systems with well-measured masses, the values implied for NGC 4395 again lie in the intermediate range between about 10,000 and a few 100,000 times the mass of the Sun. These timing-based estimates are subject to systematic uncertainties because they rely on empirical correlations rather than direct dynamical measurements, but they support the reverberation mapping results and reinforce the conclusion that the central object is significantly more massive than a stellar black hole, yet not comparable in mass to the black holes in giant galaxies. Kinematic measurements of stars and gas in the central region place further limits on the allowed mass range. In principle, the gravitational pull of a massive central object would increase the velocity dispersion of stars and the rotation speeds of gas very close to the center. However, the spatial resolution of current observations and the presence of the nuclear star cluster make it difficult to isolate the contribution of the black hole. Stellar velocity dispersion measurements in the nuclear region of NGC 4395 yield values that are low compared with those in bulge-dominated galaxies, with massive central black holes. These low dispersions are consistent with a small or moderate central mass and with the absence of a massive bulge. In practice, the stellar kinematics provide upper limits on the black hole mass that exclude values much larger than a few 100,000 times the mass of the Sun, but cannot pinpoint the mass within the narrower range suggested by reverberation mapping and variability. Gas kinematics in the very central region show complex motions influenced by the nuclear star cluster, the active nucleus and local structures, so they are less straightforward to interpret as pure traces of the central potential. Taken together, the existing measurements indicate that the black hole in NGC 4395 is an object with a mass between roughly 10,000 and several 100,000 times the mass of the Sun, placing it in a range often described as intermediate mass or as the low mass end of the supermassive black hole population. The terminology reflects the fact that there is no sharp physical boundary between categories. In many contexts, black holes with masses between about 100 and 100,000 times the mass of the Sun are referred to as intermediate mass, while those above several 100,000 or a million solar masses are called supermassive. NGC 4395 sits near the upper end of the intermediate range or the lower end of the supermassive range, depending on the exact mass adopted and the convention used. Regardless of the label, the key point from an astrophysical perspective is that this black hole is much less massive than the central black holes in luminous Seyfert galaxies and quasars, yet it powers a recognizable active galactic nucleus in a galaxy that lacks a classical bulge. This combination makes NGC 4395 an important test case for models of black hole growth and black hole host galaxy coevolution. One class of open questions concerns how such a black hole forms and grows in a low-mass, bulgeless host. Most models for the growth of very massive black holes in giant galaxies involve a combination of gas accretion and mergers over long cosmic timescales, often in environments where galaxy interactions and major mergers are common. In NGC 4395, the low stellar mass, modest gas content and relatively undisturbed environment suggest a different growth path dominated by slow secular inflow of gas through the disk. The current low accretion rate implies that the black hole is growing only slowly at present, but its integrated growth history is not directly observable. The efficiency and frequency with which gases reach the central regions over the lifetime of the galaxy remain subjects of investigation constrained only indirectly by the present mass and activity level. Another set of questions involves how the black hole in NGC 4395 fits into empirical scaling relations between black hole mass and host galaxy properties. In galaxies with classical bulges, tight correlations exist between black hole mass and the mass or velocity dispersion of the bulge. NGC 4395 lacks a classical bulge, so there is no straightforward bulge mass or dispersion to insert into these relations. When one attempts to compare the black hole mass with global properties such as the total stellar mass of the galaxy, or the properties of the nuclear star cluster NGC 4395, does not lie on a simple extension of the relations defined by massive bulge-dominated systems. This mismatch indicates that black hole growth and bulge formation are not strictly linked in all galaxies, and that different processes may dominate in low-mass bulgeless systems. Understanding whether NGC 4395 is a typical example of its class, or an outlier, requires larger samples of similar galaxies with well-measured black hole masses. A further area of active research is the occupation fraction of central black holes in dwarf and bulgeless galaxies, meaning the fraction of such galaxies that actually host central black holes. In massive galaxies, central black holes appear to be nearly ubiquitous, but in low-mass galaxies the fraction is less certain. NGC 4395 provides a clear case of a dwarf bulgeless galaxy with a central black hole that is actively accreting at a low level. This demonstrates that at least some galaxies in this mass and structural regime host central black holes. Determining how representative NGC 4395 is for the broader dwarf population requires systematic searches for active nuclei and careful mass measurements in many low-mass galaxies, including those without obvious nuclear activity. The existence of a central black hole in NGC 4395 also raises questions about feedback in such low-mass hosts. In massive galaxies, energy and momentum injected into the interstellar medium by luminous active nuclei can drive powerful outflows and may regulate star formation. In NGC 4395, the nucleus is much less luminous, and any feedback effects are correspondingly weaker. Observations of its ionized gas and extended emission lines show signs of localized outflows and disturbed kinematics near the nucleus, but there is no evidence for large-scale galaxy-wide winds driven by the active core. Whether such low-level feedback can still influence the central star formation history, the structure of the nuclear star cluster, or the inflow of gas on small scales remains an open topic. These questions are explored using spatially resolved spectroscopy and detailed modelling of gas dynamics in the central regions. In summary, the central black hole in NGC 4395 is a low-mass active nucleus with a mass in the range from roughly 10,000 to several 100,000 times the mass of the Sun, hosted by a bulgeless dwarf spiral galaxy with a low surface brightness disk and a compact nuclear star cluster. Its properties place it at the low-mass end of the known active galactic nucleus population and make it a key object for investigations of black hole formation growth and host galaxy connections in low-mass disk-dominated systems.